We'll hold off till we see if everybody else is coming. Won't take that long, I don't think. We'll get there. I'll be sending you a couple of these PowerPoints. One I created and one I basically am using off the internet. I'll look at this. So I did not put in the invitations, which I always do at the start of the semester for these Google Meets, and I will get that done, sometime this afternoon. And so in time for the next time I present, you'll certainly have all those invitations. I use them, and Dr. Buxton doesn't. Okay, but that's fine. Different material all the time. So unless, and I may have to pause to let other folks in, but I don't think we're necessarily going to be here that terribly long. And I'll show you where I'm at, first of all. So without further ado, I haven't made my own PowerPoint in quite a few years, so we'll see how this does. But this is the one that you're going to be looking at, the slideshow. Uh-oh, somebody else is here. I'll keep dinging. Hold on, we'll let him in. Letting him in. It's quite a few. I don't know if anybody else is going to be there. We may have another one. 7, 5, we'll see. All right, so if we hear that ding, we'll go back and start back with it. Nevertheless, so this is where we are, and this is just a PowerPoint. And this first one is mostly about terminology more than anything else. I suspect that as Dr. Buxton and I put together the material for the midterm, a lot of it, at least this portion of it, will deal a lot with terminology. Okay, hold on. Very good. So as I was saying, I think as we put together this first examination, then for the midterm, that's going to deal a lot with terminology. So I wanted to throw and amplify some of these things that we see that are there. Okay. And so I just want to make some generic comments about them as we proceed. If we hear another ding, and I'll know I have to get back and do this. And as I said before, for all of you later, the ones who just logged on, they're not late arrivals. It's my error. Is that I will make sure that everybody gets invited and just accept the invitation, and we're good to go with that. It just makes life a little easier. I was surprised because I was able to send you all the material, but apparently the invitation aspect, when we do these remote locations, which we do periodically, be potentially problematic. So here we go. So this is all about terminology, divisional delays. Okay, this is probably the least problematic, because when you're talking about dosages as they affect individual cells and or tissues, it applies to either. So the delay can be lethal or non-lethal. As you will see, the potential lethality of the radiation dose depends on when the next one is and if the cells have been able to recover. Okay, and there's something they call the mitotic index. And that's the number of, and this may be material you heard before, but this is the number of cells that are in different stages within the cycle. So as we look at and it'll be reviewed, the individual events of the cycle, whether it's G1, S, G2, or M phase, all of those are relevant. Interestingly enough, as you will see, the phases that are least problematic, least affected, and are G1 and certainly S phase, which is surprising because that's where the DNA is replicated, but it has to do with the nature of what the DNA is like at that point in time versus G2, the later portions of G2 and M phase, where it's very, very susceptible, and I'll comment on that as we go on. So it's really important to look at that, all the parts of the cycle, and know roughly the events and what the critical pieces are that are going to be involved. And this is, again, a dose-dependent phenomena. So particularly that initial dose and where the cells are. So if we look at a cell population, any cell, look at a piece of lung, look at the gastrointestinal tract, how many are in what stage of what? How many are in interphase? Are they in G1, S, G2? Because it's nothing that happens uniformly. So it's not, and a lot of times I'm asked this question. So, I mean, it's like when we talk about the lining cells in your small intestine slough every roughly 3 days, it's not simultaneous, it's continuous. And because it's continuous, you have cells that are in different stages at different times. So it's the accumulation of potentially lethal effects that impacts them. And so this becomes dose-dependent phenomena. And so if you irradiated everything massively at once, there would be such a tremendous amount of damage that it would be very difficult to recover from, and just the aspect of the recovery would be extraordinarily severe. So with the fractionated treatments, this is where the science comes in behind it. So that's the first nugget. The next one of these is called interphase death. Now, well, these next two are all about lethal doses. Okay. So this is occurring during interphase. So it's not during the mitotic or divisional things that are there. And there's a variety of targets that are susceptible of that, particularly, and this is the most interesting one, mature lymphocytes. Of all the cells that are mature, that are susceptible, this is probably the one that's the most unique. And I would suggest you remember, because that'd certainly be a question I would pose about those things. Here's a cell, I think the reason behind it is that lymphocyte is a cell that responds to infection. So when these mature lymphocytes will effectively can change and all of a sudden become very replicative. They can start to reproduce, and they do so, and we call it cloning. They make additional lymphocytes that either make antibodies, and that's something that happens, let's say, with COVID, with what the immunization is supposed to do, reprogram cells, put up protein spikes, and then effectively will generate an antibody response. Well, those antibodies are made by lymphocytes. And so even though they're mature lymphocytes, okay, they're going to respond. And what happens, and the other way they respond is when cells are damaged. And that's when we talk about something called killer T cells, which are known as cytotoxic T cells. And it depends on whether or not the problem is occupying a cell or it's floating around in the bloodstream or in the tissues itself. That's a different thing. That's all about immunology. But these mature lymphocytes can change. They can all of a sudden go from being non-mitotic to mitotic, number one. And number two, they have a relatively short lifespan. So what we see is what they call interphase death. So it's kind of like this apoptosis. We really don't understand the mechanism. So apoptosis is called programmed cell death. The classic example is a tadpole losing its tail as it becomes a frog. And so cells are, based on your genetic program, designed to effectively expire. And very often that's part of the growth and development process. So that's the first one of these, this interphase death. And reproductive failure means that it's unable to reproduce in the future. So this really has more of an effect long term. So there may conceivably be some cells that are able to repair. And the thinking is that this is when we see distinct DNA damage. Read that as breaks in the DNA strand. So that's another issue that's there. And as an aside, I mean, I'll send you both of these PowerPoints, the one that I made and this other one that I found. And I've had some success finding ones because they do illustrations better than I do. You'll see how badly I do it. Shouldered curves. This sort of leads into what a shouldered curve is, because you have varying responses where some cells are affected but don't die. Some cells die right away, and some cells die comparatively slowly. So most of the curves demonstrating the tissue response or cellular response to radiation have this so-called shoulder. Okay, and it relates distinctly to the undamaged cell. And a lot of times the damage is cumulative. So if it's non-lethal, they'll repair, but with interval approaches and this fractionation approach, what it does is it allows for this, we demonstrate this shoulder curve that you see so classically. I might even have I don't think I have a picture, but I think I have a picture coming up later. So when we talk about different kinds of damage, you're going to, and just to go backspace for a second, with regard to the shoulder curve, basically in the initial phase of the treatment, over time, we don't see as much cell death initially. It's kind of what it looks like. So they call it a shoulder, sort of like a hump. So the curve isn't a straight line curve. It's not. As soon as you start treating, cells begin to die. It kind of has this little hump initially that kind of is like a slower response, and then it begins to go down. I thought I'd amplify that. So involving 2 doses, sublethal damage. One's not enough. So it's all about the time interval. That's something that's looked at a lot. It's the basis, at least according to the text, for this fractionated therapy. Again, we don't understand the mechanism, probably related to DNA repair. DNA repair is something that, depending on the nature of the cell, they have a lot of capability of doing, particularly in our cells. Okay, we have some pretty advanced reparative mechanisms. So that's another factor that's part of it. So the nature of the damage, and I think you'll become more acquainted with this over time, particularly professionally, when they'll look at certain characteristic cells, do blood tests or do monitoring in between to see how well a patient is doing before the next series is ordered. Potentially lethal death, similar to sublethal. Okay. Depends on what happens afterwards. Again, we're not quite sure about what the mechanism is, but is there adequate nutritional state of the cells? And interestingly, we begin to see that sometimes that there's an improvement. So it's not quite understand improvement, not so much in cells that are dying, but a likelihood of survival or repair. So it depends on maybe on how much of the tissue and how much has been damaged, and have there been alterations in blood supply and things like that that could play a role. So it's interesting that the response isn't, you'd think that it would all be lethality, it would all kill or damage things significantly, and it would limit their repair, but not necessarily the case. And so then we also define things as radiosensitivity. And this is, to me, the biggest factor that's there, the status of the cell. So I put this, I sort of cobbled this together from 3 different chapters, from 3, 4, and 5, looking at critical terms and trying to come up and say, this is what, this to me are the talking points, the take-home points. Is it actively mitotic? Number 1. Okay, so if it's no longer reproducing, it's much less likely to be damaged, and perhaps even it would take an immense amount of radiation to damage it. That really, to me, is the impact of what's called a degree of differentiation. Differentiation is both maturity and development. So a highly differentiated cell, like a nerve cell or a muscle cell, particularly effectively exit the cell cycle. They become what we call amitotic. They don't do it anymore. Okay, they have reached their maximum part of development and or maturity, whatever term you want to use. And they're as specialized as they become. So you can't change a cranial nerve into a different nerve. It's not going to happen. If it's damaged, most likely it's going to die. That's and be replaced by scar tissue. Whereas the opposite, typical, what we call less differentiated or undifferentiated cells, continually, rapidly grow. And these are the means of replacement. All those epithelial cells I went over with you last time are like that. Okay. They're continually undergoing mitosis. They have a limited lifespan. They slough, for the most part, the lining cells. They move away from their bed. They're constantly being reproduced underneath them. As they begin to become replaced, they don't stay necessarily attached, like, say, skin cells or the lining cells in your mouth. They basically are shed. They have a limited lifespan, and they basically disappear. Probably the wrong way to say it. I guess they disappear if you're looking at a microscopic slide. When I say sloughed, they're carried out. So in your mouth, those cells, you swallow them or spit them out. In your gastrointestinal tract, you get rid of it, you defecate them out. Okay. So they go out with fecal passage. Okay. So it's all about maturity and the role that it has, and the really so those are undifferentiated cells. So when we get to stem cells, those are having they are cells that have this remarkable capability of changing into various kinds of cells, and there's a whole categories of these. That's what's coming up. So here are the populations: stem cell, totally undifferentiated, all about making other cells. Okay. In the bone marrow, if you remember the slide I showed you before with that PowerPoint of the blood, all those parent things that come off of an interesting cell called the hemocytoblast. It makes red cells, it makes white cells, down the road it makes platelets, all different cells that are found in the bone marrow. So it's very, very versatile, and the different signals will make that occur. Embryonic tissue. That's why they'll utilize things like cord blood, and you'll retrieve that because it will have these embryonic stem cell tissues that and nowadays the theory is that if you can do various treatments on them, grow them and inject them into people to either growing organs, or what we would eventually do in the future, or be utilized to try to induce cells to reform that maybe haven't formed very well. Damage that can be done, and particularly being utilized in children. And it's an interesting idea, if you don't recall it, that's what my granddaughter, who's 4, had these kind of cells injected into her on 2 occasions at Duke University. Very expensive. It's not something that's typical health insurance covered. It's not something you know the results of right away. And so I'll get more feedback on that, probably in a year or so, things like that. So if you're interested, something you can sort of look up and learn a bit about. Transiting cells that are going from one place to another, and sometimes they change as they're moving. And again, we look at the bone marrow. So red cells and white cells. White cells, typically there's a maturity process. Most of the time when a white cell leaves the bone marrow, most of the time it's fairly mature. In infections, in diseases, in injuries, our body makes a big effort to repair itself. So sometimes it puts out immature forms. That's a problem. The analogy that I was taught, it's sort of like there's a battle going on, and your white cells are the troops that fight the battle. And if you're losing the battle, or the battle's just started, you may not be ready. So you put out raw troops that haven't been trained. That's what an immature white cell is. It can't do the job effectively. So will be some maturation as it moves away from the bone marrow, yeah, and that's a cell in transit. Red cells, basically their whole job is to carry oxygen, and what they do is they continually mature. And so part of their maturing process is to shed their nucleus and shed all their internal structures called organelles. So they do that. And so it's really significant. And what happens with regard to that is once they're mature, then they function. So red cells, we have so many of them, even if we see them changing in transit, not a big deal. Now, the reticulocyte's an interesting cell. It's a red cell that we always have about 1% of them. If we count all the red cells, about 1% still have organelles that are inside, and we call them reticulocytes. We do that to see how well the bone marrow is doing. If the number's too low, then the bone marrow is sluggishly putting out stuff. If it's too high, it's putting them out too rapidly. And that may be a means of testing to see what's going on in the bone marrow. So we do a thing that it's relatively good. It's done with a standard blood test. They actually are able to count the reticulocytes, called a retic count. And again, ones that stop doing anything, nerve and muscle cells, they don't divide. Which brings us to these 5 different categories that are, and again, these are the types of things that are easily testable, very much definition, and I think it's part of the stuff that you need to be familiar with. And so we have vegetative. Now, in cells, vegetating is fine. Okay, it's not. You don't compare it to someone in a permanent vegetative state. So we think of cells growing and replicating. They're actually vegetating. In this case, when it comes to a cell, is rapidly dividing. They're undifferentiated. Those are the typical stem cells, bone marrow cells. We see them in some other locations, and particularly in fetal cells and things like that. And those crypt cells, those are the ones that I talked about and showed you that are those crypts, those little indentations in the lining, particularly in the small intestine. We have so many of them. So they are the most sensitive. And now, so this chart goes from most sensitive to least sensitive. The differentiated ones, okay, they can still be actively dividing, but they're a little bit more differentiated. And so the example they give you are sperm cells. So when a sperm cell is born, it's very, very sensitive when it just starts, when it's just produced in the testes. And it goes through various stages of differentiation as it begins to become a mature sperm cell, which are comparatively less sensitive. And so what happens, it's still actively dividing as it's changing, but it's gradually becoming more differentiated. And then in the connective tissue, now connective tissues have a certain amount of protection because they're denser. It's harder for things to get through, and they don't divide continuously. So fibroblasts, which can become change and make more fibrous tissue or cartilage tissue or bone tissue, are like that, as are the linings inside of blood vessels. And the blood vessels are surrounded by layers of additional tissue like smooth muscle, which is not sensitive. So there's layers of protection, or there's an abundance of structures. And now when they look about reverting post-mitotic, relatively resistant and the oddball is that mature lymphocyte. Okay, so it has the capability of undergoing mitosis if needed. Liver cells are like that as well. If there's damage to the liver can replace itself fairly easily, unless it's so significantly damaged by toxins like long-term alcohol use or chemicals or things like that, where now the liver dies and they end up with cirrhosis and have to have a transplant, something along those lines. But so these are most of the time these cells that have effectively exited mitosis and are fairly mature are not nearly as problematic. And then the highly differentiated nerve and muscle cells are. So they're sort of, again, the oddball to the rule that's there because they've exited the cell cycle. And so we also have to look at the different tissues and how they respond to radiation. So when we talk about an organ or a piece of tissue, there's some terms. We call the parenchyma. That's, to me, it was always the meat of the tissue, the cells that do the job in the organ, versus the stroma, which is the support tissues, blood supply delivering oxygen and nutrients, carrying away waste products, and connective tissue that kind of gives it its structure. Like the kidney's got a ton of functional cells, but it has to have a ton of structure in order to do the job. So the cells have a parking place and an arrangement. And so they both play a role in the response to the tissue that are there. And so this is my effort. Notice the shadow. My picture taking wasn't so good. So here you can see ones that are very sensitive: mature lymphocytes, erythroblasts, and this comes right out of the textbook. The spermatogonia, particularly in its early stages. Then varying cells, granulosa cells, myelocytes, crypt cells. And so these are cells that you're going to see, the granulosa and myelocyte cells, they're in the bone marrow. So the granulosa cells make the granulated white blood cells. Those are different kinds of white blood cells. And the myelogenous cells are a little bit different. They're similar to that. The crypt cells, and particularly the epidermis down in the base. And that's that example of when there's not your epidermal cells, skin and lining, there's not a lot of protection comparatively speaking. They're pretty much exposed. And then as we work our way down, lining cells, these are the ones in blood vessels. Deep in the gastric glands, the stomach's a little bit more protected. They're considerably deeper. There's a lot of material and fluid within the stomach. And then the building block cells making bone and cartilage. And then when you start to get to spermatocytes and spermatids, those are more advanced sperm cells. The egg cell's kind of an interesting one. I looked that up. Only if you would get direct radiation into the ovaries, because once it's matured, I don't think it's nearly as susceptible. The big problem is when there's it's exposure, like it's, let's say, shielding somebody taking x-rays, the damage can be cumulative, particularly if there's a lot of x-rays in time, and particularly for, if someone is pregnant, then obviously there's a significant damage. But interestingly, the eggs are pretty well protected. There's certain distinctions in the cells we call follicular cells, where the egg is being produced that may be impacted. And then you can see once you have full fibrous and full cartilage, muscle and nerve cells not going anywhere. And for some reason, and this is when we begin to get later responding cells that are there that are interesting about it. So again, cells classified by decreasing radiosensitivity. So again, the mature lymphocytes, the erythroblasts, spermatogonia, a little bit less granulosa, intestinal crypts, then endothelial lining cells, glands, same kind of stuff we saw before, sort of the reverse. And then we begin to get lower and lower. So once they're in that site stage, they have pretty well become mature cells. And then these are non-replicating at all. Additionally, there are things that are involved that actually enhance the response to radiation. Number one, it creates clearly oxygen. And there are procedures where, at least historically, it was administered. And I don't know about the procedural aspect of it. The mechanism is unclear. Is it free radicals? Likely. Is it repair less likely in the presence of oxygen? Yep. So we don't know why, but those are the theories. That for some reason, either there's additional free radical production, or there's some aspect of the oxygen that, for whatever reason, limits the repair mechanisms. And so you can see some of these, and again, this is another textbook thing, and I've got to find a better way to put them into PowerPoints. But here you can see it's sort of like the surviving fraction that kind of creates that little bit of a hump. So when they don't have a lot of air, okay, it works, it isn't quite as effective initially versus when it is very well aerated. Look at that. And the same thing that you can see here. The degree of aeration does play a role with regard to this dosing and things like that. And so when we look at the actual oxygen tension, okay, as that becomes, you can see the increasing if it's very low, but as we begin to increase it, look at the, and we're looking here at a scale in millimeters of mercury at 37 degrees Celsius, normal body temperature that's there. These are some other agents. I'm not as familiar. I don't know what I'm familiar with certainly the materials, mesonidazole and halogenated pyrimidines. Okay, pyrimidines are part of the building blocks. They're the C's and the T's of DNA, cysteine and thymine, also uracil. When you add a halogen, it's a toxin, okay? So it's interesting that would have sensitizing effects. And the azoles are, interestingly, antifungal agents that have a lot of side effects. And so I'm not as familiar with them, but I mention them for the sake of completeness. And interestingly enough, when we want to protect things, they use what are called sulfhydryls. It must be that the sulfur and hydrogen play some role in competing for free radicals. Again, they don't know the mechanism. There are two amino acids that it really the same amino acid in a different shape, called cysteine and homocysteine. Okay, which is now that don't mistake that for cytosine, which is a pyrimidine. Okay, so the cysteine amino acid is the one that has the sulfhydryl group, and it appears in different conformations. And so again, this is the phases. Remember all the phases. Less sensitive in G1, least sensitive in S. And most of us believe, the authors that I see, is it had, and from the readings I did, I shouldn't say most of us, but most of the people who have studied this, think that the DNA, when it's supercoiled, is much more sensitive. It's easier to break those DNA strands. So in S phase, it's basically in this uncoiled or quote unquote relaxed form. So we actually don't call it chromosomes, we call it chromatin. When it perhaps is early starting as late G2, and I suspect this is why G2 and M phases. M phase, we begin to see the chromosome supercoiling, which means in late G2, they're starting to supercoil. That's kind of what's going on. And I would suspect that that's the underlying biological factor. And then the ability of repair between doses. So part of the logic to increase doses when fractionating, and that's basically everything I had to share with you on that particular slide. And I have a little bit more, so let me just escape from this and show you the other one that I had working on. That's there. Just for a little bit, I just want to go over, make a few comments, and then we're done. No problem at all. I have it over here. Sorry. So, and I'll send you this link as well. This slide share, I guess you have to do something to get it. So you're going to have to look at it this way as best as you can, but I'll show it to you. So you can download it, but you have to register, and I haven't done that yet. And so this is really just another one I found pretty interesting. So its effect on normal tissue, damaging cells. Okay. So nausea and vomiting hours after, particularly abdominal. Fatigue. I've always assumed, I mean, fatigue is your body's trying to fight damage would be one reason, but fatigue is interesting. And a lot of times it probably has to do a fair amount with effects on blood cells that are active, either on the bone marrow itself or on those lymphocytes. Because I've experienced that when I was very anemic. And so I wonder if that plays a pivotal role. And normally it doesn't come up that rapidly, but I suspect this does. And inflammation or vascular leakage, depending on what it does, you can have swelling or redness, which are the first. When cells are damaged, they leak fluids. And when they're damaged, they release chemicals that summon other chemicals that create inflammation. Okay. And somnolence would be a really distinct lack of activity, almost no activity or no desire to become active after cranial. I'm not familiar with it, so I would reserve commenting on it. Okay. So tissues are integrated structures. Most of them, death and birth, are balanced. So are they inherent? And this gets back to what we just discussed. Are they radiosensitive? What the tissues are doing and their organization. So these are just individual factors. So the relationship has to do with how many cells are affected. Okay, some tissues no effect after small doses, but there's typically, as there is in a lot of things biologically, a threshold level. Okay, so a few cells and a big amount of tissue are not going to create a significant damage, and of course the time becomes a factor as well. Okay, so as cells then that were affected try to divide, that's when the death comes that are there. So again, rapid cell turnover, rapidly replicating cells, intestinal, skin, etc. Okay, those that don't, not so much. Different, it's all about those kinds of things. And that's sort of an interesting nugget. As they're starting to differentiate, they're a little more resistant than stem cells. That's sort of, you recall that distinction between those cells, those differentiating cells. They're not quite the same, so they're starting to change. I think that's an important effect. And then early and different effects, early and late, different patterns, okay, different dose response curves I'm not as familiar with, okay, and then there's early and late effects. I'm just commenting on that. Early, skin, GI, hematopoietic, just what we talked about before. Late effects, slow, and these are tissues that don't replenish themselves, if at all, the heart and central nervous system, lung much more slowly, kidney much more slowly. Is there replenishment that goes on? Absolutely. But not nearly as rapidly as one would think for an organ like that. And as you can see, early, because there's more stem cells available, and it may be completely reversible, as opposed to late damage. So when the damage is categorized. So The late effect, and again, the initial effect is usually due to the direct effects of the radiation, where the later effects are due to the so-called indirect effects. So the reactive oxygen species, and they get into the science behind it. Again, these are typically the superoxide radical, inducing inflammation, inducing vascular changes, metabolic changes. So all of this, there's a lot of science behind that as well. Okay. And then we look at the fractions of cells that survives, okay, can determine the success or failure, and how tolerant the ability of cells that can clone themselves to maintain sufficient numbers so the organ can function, okay. And it depends a lot on the organ itself and if there are any pre-existing damage. So there's a lot of science that goes on between is what I'm trying to underscore. So as you can see, certainly anatomically, and without getting into all the anatomy, and these are just some wonder why the kidney, the liver, and the lung, there's an interesting, they're structurally well organized would be the way I would describe it. Okay. And so here we can, when we study anatomy and physiology, we can look at these structures, and there's many of them, and they function independently, but their organization, as opposed to these things which don't have a lot of organization. I don't know if I'd include the spinal cord in that with regard to it as well. And they're just showing you some of them. I don't think we need to go over these illustrations that are there. And then this deals mostly with exposure. So, related to specific exposure things that are measurable. Okay. And other organs that resemble it. And again, this gets more into different, more specific things that I'm not able to discuss with you sufficiently. And it's noteworthy here. So when there's why most people recover from the diarrhea, vomiting, etc., has a lot to do with the fact that that surviving crypts, those cells can move all over the place. So they can repopulate even neighbors. And I think that was an interesting note. And everything else here is more specifically dose-oriented. It's not for me to do today. So I'm going to conclude and send you these links to these if you want to review them again, the PowerPoint that I have, as well as this PowerPoint that I've sort of just used for some basic comments. And I think that'll be everything. So thanks a lot. If you have any questions, feel free. I'm going to start to generate some test questions. It means I'll be generating some type of study guide with it. And I'll confer with Dr. Buxton about that probably sometime on Monday, usually when we confer. So thanks again, and bye-bye.